Hi, good morning, everyone. This is our final project, the solar absorption chiller. These are my teammates, Robert Martin, Juan Sabel, and my name is Miguel Williams. Our advisor is Dr. Andrew Stramantic. So, for our project, we wanted to have an air conditioning system which combined technologies both involving solar as well as with solar absorption chilling technologies. Here's Bobby to explain the driving force as to why we picked this.
Okay, so in the senior design project components, you either have to invent something or improve on an existing design. We chose to improve on existing design. 99% of the space cooling worldwide is provided by vapor compression technology. So we found a need to find an alternative to that. Obviously, renewable energy is growing. The necessity of it is driving force in a lot of design work. Using the sun is gaining popularity in heating water. PV panels a little less efficient, but they're both combined in this system. We also want to reclaim the heat that we reject from the system and reuse it in the system to drive it. And in doing this, we're going to reduce carbon emissions. We're not using a standard refrigerant that most systems use, the vapor compression technology uses, so we're eliminating the chlorine-based refrigerants as well.
Okay, so on a global scale, one of the key benefits of our project, for one, a reduction in the carbon footprint. There will be a reduction in carbon and chlorine emissions. We would like to have this applied in somewhat remote or disastrous areas, where it is, they can really be impacted by this. One of the key aspects of our project, say you have an area that suffers really intense heat, regular compression systems tend to break down, tend to burn out in those type of areas, whereas opposed to our project, it actually feeds off of the solar energy. There will be, of course, a reduction in electrical consumption. In terms of the commercial market, let's say here in Miami, for instance, when you look at your electric bill, about 75 to 80% of that is just from your AC system. So our project is to deplete on your expense in terms of paying for that electricity. And again, we're taking energy that is free and we're making the use of it and trying to improve on that energy and how beneficial it can be to us. So of course we'll have user manuals. As we said, this is for a global scale, so we had it in English, we had it in French, we also had it in German.
So the design process for this project, we had to analyze the system, size it, and then select our components. We're using the absorption chiller, which our system uses a water-fired system, which uses heated water to drive it. We're also using PV panels, which uses solar energy to make electricity, and then we're using the thermal radiation to also heat water to drive the generator. So the given parameters that we're assuming at the beginning, we had to use manufacturer specs of the actual heat that we're using to input to the system, and also what our capacity of cooling, which we chose a 5-ton system for this case because it's more compact. We're talking about using something that's on a global scale that we can move around a little easier. So based on our assumed parameters and assumed assumptions of how the system will work, we had to choose a quality of the lithium bromide, which is the salt within the system, and our temperatures, heat input, drives that. So standard units that use 200, 250 degrees, we wanted a system that only requires 120. So we had to lower the pressure inside the vessel of the generator, which 80 millimeters of mercury can boil water at 120 degrees, which is easily to achieve. And that leaves lithium bromide quality of 50%. Any higher or lower, it won't work right. So we chose 50%, which is exactly where we want to be. Again, 120 degrees to drive it. So in actually selecting the components, the absorption chiller, like I said, is a water-fired system that shows the manufacturer's actual heat input and rejection by the condenser and absorber. And that 42 kilowatts that's rejected by the condenser and absorber, that usually goes to a cooling tower and is expelled to the atmosphere and wasted. We want to reclaim that. 42 kilowatts is quite a bit. When you see the generator only requires 25, we can use a heat exchanger, absorb that heat, preheat the water from the me the solar water heating system and make it easier on that. So in choosing the water-fired chiller, we had to do a heat transfer analysis, which standard engineering calculations. We assumed mass flow rates that given by it, also the heat input by all the components, which you saw before. The delta T, which we can achieve by slowing down or speeding up the water, we will choose pumps that'll be able to satisfy that. These are the mass flow rates that we ended up finding with our desired temperature differences and heat input and output that we wanted. Taking into consideration, changing the temperature is going to change the capacity and also the flow through the system. So we chose the Yakazi absorption chiller, which is the water-fired chiller, 5 ton, one of the only 5 tons out there, but it's perfect for what we need, producing 44-degree water, which is used in evaporators or air handlers within a building to provide conditioned space. And using that most mass flow rate that we found, and using TACO pump selection application, we chose the capacity that we wanted as far as GPM and also the head foot capability. And these are just the 5 pumps that we found within the system to pump between the evaporator, between the condenser absorber, outside the system from the solar water heating. And the total kilowatts that we need for just those 5 pumps is 302 watts.
So in terms of generating the heated water to power our chiller, we look at different technologies that were available, and we selected that we were going to use solar collectors. And then we set up some conditions that we found are, we tested here in Miami, so we took the conditions here in Miami to make testing and to determine what was the best kind of solar collector that was available for our project. Basically, there is the Solar Rating Corporation, which help us, determine. They test all the different solar collectors that are available, and they create efficiency equations that we use to determine what was the best fit to our design using the conditions that we have. So basically, what we see here is the different technologies. We have evaporated tubes, we have flat plate solar collectors, and we ended up choosing the flat plates, the glazed flat plate collectors, because for delta T, it was the best. We could get the best efficiency. If you look at in these 2 tables, we compare 2 different technologies. We compare evaporated tubes in this size using the equations of the Solar Rating Certification Corporation. And on the left side, we look at the flat plate collectors. And we can see here, same that we saw on the graph, that the flat plate collectors have a better efficiency for the conditions that are present in our projects. So once we found what was the best efficiency that we could get, we found the amount of panels that we needed to power the system. So, and we used that using thermodynamics equations. So we found that the energy that was coming into the system, was related to the energy coming out minus the losses. So we came up with these equations, and we found that we could find the area that we needed from this equation, which is equivalent to the mass flow, the heat, the specific heat of the water, and the temperature difference, plus the efficiency of those panels. So we ended up selecting the Solar Skies SF16 flat plate collectors, which have a gross area of 15.45 feet square, and this is the equation that is given by the Solar Rating Corporation to determine the values that we found on the previous graph.
Okay, so where we had solar thermal collectors which provided heat from the solar energy we acquired, we also had PV panels or photovoltaic panels that acquire that energy to produce electricity. The purpose of using these panels were to power the pumps to pump water through the cycle. So where you see here, we have the graphs of some testing we did on some PV panels right here on campus, on that end by the gazebo. We ran some tests. We also had a charging station where power was used to charge some batteries that we had. Where you see here, we did 5 different trials. Sorry, we did 6 different trials, and they would go in 4-hour periods. So where you see here, this was for our 4th trial. This is the power rate that we got. We can also see the voltages and the amperes we acquired for the different hours during that period. And from our research and analysis, These were the panels we selected. It's called the SunPower X Series solar panels, as you see there. And each panel produces, well, sorry, the pumps required 350 watts to power the system. Now, of course, we had to consider during low times, we will be able to produce this amount of power, so we decided to go with a 1 kilowatt system. And here, the panels we selected, these are the efficiencies. We selected the SunPower, as you see, 21.5% efficiency as compared to the other panels. You can see that's a wide gap with a cost of $2,300.
So for the system modeling, we wanted to see how the system would look like if we were going to build it. So we use SolidWorks to create the parts that we use for the system. So here we saw, on the previous slide, we saw the solar chiller. We saw, I think it was the waste heat recovery. We have the PV panels, we have the flame plate collectors. We have a storage tank, we have pumps, and we basically have here the system layout, which is...
So we combined all the components. This is an actual manufacturer piping layout, but this is exactly what our system would look like, where the solar heat collectors absorb the water, stored in a tank. It's supplied to the water-fired absorption chiller. The waste heat recovery is in series with that, which will, in our system, preheat the water, or we can actually use it to drive the generator entirely, providing cold water to the air handler to condition space. So this is the actual piping layout that we did based on that and based how the components are combined. This will be within our portable system. This is the final design of our system, which the PV panels can move around depending on location, but that system is on a complete skid with the flat plate collectors above it to maximize efficiency. This is the components that we selected based on all our analysis and manufacturer specs and cost. Obviously, the water-fired chiller looks a little expensive, but it's one of the only ones out there, and it's coming from another country. It's to ship worldwide, it gets expensive. It's very critical. The solar skies, we chose 4. Again, redundancy, not necessity. 80-gallon tank to store it. 5 take-out pumps, which the solution pump is number 6. 3 panels, like Mikhail said, we want a total output of just around 1 kilowatt, just in case on the low conditions. You can also store the energy and drive it during off hours. But if there's not enough heat during off hours, we can implement a resistance heater within the tank and actually supply that hot water and drive it off the waste heat recovery. Controls and piping, total cost of around $40,000. Again, most of it's from the chiller itself. So our prototype, obviously buying a $25,000 machine is a little expensive, but we actually developed the components and piping layout and actually combined everything where you can see our PV panel and solar water heating fully functional. This is an evacuated tube system that's similar to the flat plate, which does the same thing, collects heat, heats it up. We can measure the temperature now and actually analyze that, analyze the PV panel, which even using a lamp is producing 3 volts, and our cost on the prototype.
So for the standards, we wanted to make sure that all the components that we use for the design, comply with some kind of standards, because we wanted to provide safety. This equipment is going to be handled by people, and we want to make sure that everything is safe to use. So we basically make sure that all the components comply with the ISO standards and all of those standards. So here's a table of the standards that were used for the design of each of the components, and that we look at that.
So in conclusion, obviously doing a year-long senior project, it takes a lot of time, a lot of effort from all the group members, but it was nice to actually combine the work that we've been working on, or the coursework that we've been learning, where we can use the actual equations and applications to analyze a system like this, to completely design it ourselves. We didn't necessarily build a new invention, but combining things that we know about and can use, it was nice to do. And in our objective, we wanted to reuse the heat, which is gain popularity, obviously, because it's free energy as well as solar. We wanted to use those components. We found a way to do it effectively and efficiently as possible, where we use that thermal radiation to heat the water and generate electricity in the PV and solar water heating. Also, we can keep working on this. Hopefully we can eventually buy a system like that and actually implement it. But future senior design projects can maybe find a way to heat that water maybe more efficiently. I think we are going to design.
Okay, so we would like to further increase the efficiency while reducing the cost, because cost is important, especially when we look on a commercial scale. Obviously, one of the most important factors is what is the cost, you know. So we would like to reduce that, obviously, and we would also like to, because we said we would like to, you know, transport it, take it to different areas in need. So obviously we would like the smaller size possible, so it'll be more portable. We like to, with that efficiency, we like to improve both the PV efficiency and improve the thermal storage that we can have for the system. One major improvement that we like to implement are what are known as hybrid panels, because PV panels, for instance, they tend to not absorb as much heat as, you know, it can. It tends to expel a lot of waste heat. So to avoid that, we like the hybrid panels, which involves both PV technology and solar thermal technology, so that heat won't be wasted, it will be collected instead. And we'll also like to possibly add a solar tractor on it, where it can follow the angle of the sun to absorb as much heat as possible. Any questions?
Could you go back to your standard slides, please?
Yes.
What about specific HVAC slide, standard? What HVAC?
Just the absorption chiller, which is up top, you will listed in the info. We didn't do anything for, you mean the air handler? Or
Yes.
you're talking about the chiller?
Air handler.
We didn't do.
Okay. And in the real world, how does this compare cost-wise to a similar apparatus?
It's more expensive than the vapor compression technology. The water-fired chillers.
So how can you make it competitive?
Because
No, the question is how? How can you make this?
Well, the thing is that this system is intended to parts of the world where there is no easy access to electricity. So we have a self-contained system that will work without any grid or anything. It's just the unit, and it will work by itself. That will be a plus compared to other technologies that will need some kind of power to function.
So you're saying the cost benefit here is a lot better than something comparable in the real world?
In the long term, reducing that electrical consumption, yeah, it'll be a lot better.
Can you give us numbers with that? That would help a lot, right? So it may be more expensive to make in the beginning, right? But over time, over 10 years, you can calculate the energy cost difference, right? Especially if energy costs keep going up and up and up. This is free energy, right? Basically. So this, you have an initial investment of $41,000, but you don't really have any other money past that, right? So what is the cost of a chiller now? Maybe it's $10,000, but it's $50,000 in electricity cost over time, right? So that helps a lot to sell your design.
Sure.
Okay, and I have, again, a question for each of you, and I'll start here. In the solar cell analysis, you came up with an efficiency of 21% for the best situation.
Yeah.
Why did you select not to use it in your final design?
In the final.
The final design, you're using a different system than the one that you had proposed.
No, that's the one that we're using.
That's the only reason the 21.5,
Okay.
the sun efficiency, the sun power.
The sun power, the last one.
Yeah, that's what we're using.
Okay. Can I step off that one? Okay. Next question. You made a statement of improved design over what is in the marketplace today.
Yes.
I'm looking at commercially available equipment here. What did you do that's improved over what you could commercially buy today?
So everything that we used is commercially available, and even all these components, we use commercially available products, but combining them the way they're combined is not used today. The water-fired chiller, Yakazi is one of the only companies that make something like that. It's just coming out. They're not really using that. They usually use direct fire, something like that, actual fire or propane, some kind of gas that they fire. So using the water aspect is something new, and we found that using this solar heat collector can generate the temperatures we want. So it wasn't that we designed something new, but how they're combined is new.
Okay. And did you end up with a fully functional finished prototype?
All this is fully functional, but the absorption chiller, no, we don't have anything.
So what happened there? Why didn't you develop a
Well,
prototypical?
building an actual absorption chiller is not, using lithium bromide or building the vessels. I actually asked Yakazi for the specs inside of the system so we could try to build the vessels, but they told me it was, what's the word I'm looking for?
Proprietary.
Yes, something like that. He told me he couldn't give me that information.
Proprietary.
And you can go back to the science to figure out how to build that?
Well, sure, I know there's usually stainless steel vessels, or we started buying some of the piping. They have an icy ball system which has two of the actual vessels and generator, but that uses an ammonia system, and heating that up to any kind of temperature that's under 400 pounds of pressure, and I'm not going to work on that knowingly that, you know, it's harmful to us if it explodes. If we don't do it right, you know, combining that is life safety at that point. I didn't want to try to build that. Building it with the lithium bromide like this system does, that the manufacturer does, is not something that we could have done, knowing how it's combined. You know, we tried to ask them that. We don't know how it works inside of it. We know, you know, the parameters, but we don't know how it works inside.
The last set of questions.
Yes.
If I wanted to use this on my home, and I have about a 2,000 square foot home, what would it look like and in size and scale?
Well,
To air condition my home, you said.
for your air condition your home. The thing will be, we have to redesign the system because we'll have to create a new layout for the piping. We'll have to create determine how big your house is, and determine if the power that we generate with this system is enough for your house. The other thing is that this system was not intended to, you know, to houses here in Florida where we have, you know, power available. It was more intended to remote areas where it was hard to, you know, obtain electricity.
Okay, that system that you proposed here for about $40,000,
Right.
what was its expectations? What was the design criteria that you put that together for? Was that to air condition, how many square feet?
It's a 5-ton unit, so it'll be at 3,000 feet square, 2,000.
So I'm going to spend $40,000 on a system to do 2,000 square foot air conditioning.
Yes.
That's-
But I actually believe that you said a 2,000 square foot home. I believe it typically uses like probably we say like a 3-ton unit. Those units tend to be about like 3 tons, like smaller scale. Use 5 tons for 2,000.
Yeah, about 5.
I think what our intended purpose wasn't a residential application. We're talking about something that is used on a global scale, remote areas, like you said, but disaster areas or military, something that, you know, isn't necessarily permanently applied to a house. A condenser is very small, and I know an air handler is very small in the system. This is a little bit larger. It's, what, 15, 30, it's about 30 feet wide, which is a little big for a house. That's why, you know, implementing in a house maybe isn't necessarily or possible right now, but it's something that maybe when they improve the efficiency, like hybrid panels that make it smaller, or even maybe upgrade in the waste heat recovery so we don't need so many flat plate collectors, it might be something that we can power a house, because just the absorption chiller isn't that big. It's 6 foot tall, which is something that they can have, you know, I would keep outside, but it's something that's smaller. The other stuff is what's big, the storage tank, the solar heat collector, all that stuff is big.
Okay, thank you.
Can you go to the design of your actual prototype? So you had a slide. Yeah, next one, if you think, right? So you have that, and then can you go to the next slide really quick? Yeah. So you only had one slide on the stuff that you actually did, right? On the actual now, the other stuff is good, right? You did some analysis, but I'd love to see more about your prototype and how that relates to some of the things that you guys have learned, right? So I understand you can't build the entire system, even chill a small box or whatever, but I look, you're outputting numbers. What are these numbers, and how do they relate?
What you're asking?
Yeah, just really quick, right?
Well, the analysis that we did, like you said, was the ones here. This is a small one just for being able to bring in here.
Okay.
But this, actually, when they both absorb sun or light energy, they heat up the water. The water coming into the system, this is only a 4-tube system, which I think the flat plate was around 10 or 12, so much bigger. This is small, it's a demo, it's, you know, good for showing, but it actually functions where it absorbs the thermal radiation and heats up the water. This could heat up the water up to 150 and 180. So this is sufficient, but the amount of water is, you know, the key.
Right, so all of that, I would love to hear all about that, right? You guys spend $1,000 of your money on this thing, right? To make this. take the principles that you learned in the large-scale analysis and tell me, try to predict what that exact increase in temperature would be, and then measure, right? That's the whole point of all of this stuff. Especially if you make a device, you know, I'd love you guys to use it, right? Not just put it together to put it in front of us. I mean, that's not as important, right? Okay.
I have one last issue. Do you have a slide on the global learning component of your project? Let me take a look at that, please.
It's on the, lower components here.
All right, so what addresses perspective, what addresses engagement, and what addresses awareness? Talk to me, tell me.
Can you repeat what addresses perspective?
Yeah, there are three criteria for global learning, right? Awareness, engagement, and perspective. What you have listed there, tell me which addresses which one of those criteria.
Okay, well, for awareness, I would say, well, from regular systems, we have a lot of carbon emissions as well as chlorine emissions. So the fact that we're depleting on that, because it brings up awareness on that, so we're depleting down on that fact. The main perspective of this, like we said, like one mentioned, not really so much as to apply here, but to apply to places that need electricity. So our perspective is to, you know, to help those areas in need without that electricity. And you know, it runs on its own once we have that solar energy. And what was the third one, sorry?
Well, you should be aware of the
Yeah.
criteria.
Yeah.
Awareness, perspective, and engagement.
Yeah, and
And, just as a corollary, were you aware of the criteria that we're using to evaluate you?
yeah,
Okay, all right, well, proceed.
yeah, and well, let's see, and well, I mean, part of the awareness again would be the electrical consumption, but I would say.
All right, so obviously you're having difficulty answering the question. So can you understand what we're dealing with back here?
Yeah,
Okay, we have to interpret what you've got there. That should not be the case if you're aware of this evaluation criteria we're using. So you want to be very cognizant of that, especially in the real world when you're given a set of specifications to design something, to meet those specifications. You want to make sure you're meeting each and every one of those expected criteria and prescriptions. All right, just take that into account. You have something?
I'm good.
Okay, all right, that's it for me.